All right, so we have looked at the Calc 1 version here of L'Hopital and pushed through that. Now since we've learned more about natural log and the exponentials as we're working these problems, now we can expand our L'Hopital to these indeterminate forms. So an indeterminate form of 0 to the 0, 1 to the infinity, and infinity to the 0. We can look at all of those and then manipulate those to do L'Hopital. Kind of like how, let me scoot back a little, we took this problem right here of 0 to the infinity in Calc 1, manipulated it so you could do L'Hopital. We are going to use these forms and manipulate them so we can do L'Hopital. All right? Okay. That's why they're still considered indeterminate forms. Now remember, it always has to be a limit, so we're going to assume the limit as x approaches a of f of x to the g of x. Looks familiar, right? The tower functions of these told me I was finding a derivative. When you take a limit, that's your indeterminate form. You have this operation associated with a function to a function. That's where we're working here. Okay. And it has the indeterminate form of 0 to the 0, 1 to the infinity, or infinity to the 0. All right. Then step 1. L is equal to g of x natural logs f of x. All right. Our goal here with this step, if you have a function to a function, I can't mess with something when it's up here in an exponent. So we introduce natural log to get g of x out of the exponent. Okay, so we use logarithmic properties, and because we're using logarithmic properties, I now have this L. So L is equal to this new thing whenever I use my logarithmic properties. All right, then we're going to go back to the example, kind of like what we did previously. Then put this into a rational expression to use L'Hopital to get my 0 over 0 or that infinity over infinity situation. All right. Same thing like the infinity times 0 deal. Once you have something that's multiplied, then you're going to manipulate that into a rational expression so we can actually use L'Hopital. Then step 2 is when L is finite, right? It's a specific number. It's finite. It's a particular number. Then the limit as x approaches a of f of x to the g of x is equal to e to the L. Let's talk about inverse functions for just a moment. I introduce natural log to this because I have to get that out of the exponent. Well, you can't just introduce a function and let it go. Because I introduce natural log, I have to, as my final answer, put this in terms of e because they're inverse functions. Natural log and e cancel each other out, right? Right. So because natural log and e cancel each other out, then this L here has to be the exponent of e so that I can't just introduce a function and let it go with it. Does that make sense? Okay, because I'm introducing because I'm introducing natural log, I have to counteract that with the e in my final answer. Okay, if L is infinity, I'm going to put equals. Get rid of that little extra fella there. Then the limit as x approaches a of f of x to the g of x is equal to e to the infinity, which is obviously infinity. No duh, right? Because whatever this value is that L is, it goes as the exponent of e. And so if it's infinite, then my whole answer is infinite. If L is equal to negative infinity, then, put my same notation here, instead of writing the word then, limit as x approaches a of f of x to the g of x is equal to e to the negative infinity, which is the same thing as 1 over e to the infinity, right? Oh, that's an 8. Sorry, you're hollering at me. Great job. Is equal to 1 over e to the infinity, which we know equals 0. Right? So that's our basic knowledge of e. So what we know about e, and the fact that we have to put e in there because I introduced this natural log, so e has to be part of my answer to counteract the fact that I'm putting that operation in there. Okay, let's do some examples so we can see what's going on with it. We don't have room at the bottom of that to pull that off. So let's try a new page. Here's example 2a. I'm going to take the limit as x approaches 0 from the right of x to the x, right? Function to a function, and I'm doing limits. So if I plug a 0 into this, this would be 0 to the 0. There's my indeterminate form. Now rewrite this so that I can put it in terms of L'Hopital. So if I bring that x in front, I have to take the natural log of my base. And this, I did it, didn't I? Oh, you guys, where'd that limit go? I don't know, because I didn't write it. You can't lose that limit. It's super duper important. And I lost it. Come back, sweet little limit. I miss you. All right. Now, remember what the graph of natural log looks like? Right? So as it approaches as it approaches 0, then I'm going to negative infinity. But I'm approaching 0 from the right. That's why I have to approach 0 from the right, because of the natural log. Here with this x is going to go to 0, so this is the same thing as 0 times negative infinity, or 0 times any kind of infinity there. Then I know that's my indeterminate form, and we rewrite it. So L is equal to the limit as x approaches 0 from the right of the natural log of x over x to the negative 1. Right? And then that's where I get my infinities. Right, 1 over 0, because that's what's happening down here. 1 over 0 is going to get me that infinity part. Okay. 0 in the denominator, number on the top goes to infinity. Just making sure we still remember that. Now I L'Hopital. So L is going to be the limit as x approaches 0 from the right. The derivative at the top is 1 over x. The bottom is negative x to the negative 2. I'm just going to write it like that for now. And simplify. Right, so simplify this rational expression. L is actually equal to the limit as x approaches 0 from the right. I'm going to write this out a little bit more just to make sure you see what's going on. Negative 1 over x squared. Whenever you take this, that's the same thing as 1 over x times this negative x squared over 1. Do you see how that happened? Right? Multiply by the reciprocal, and you end up with that negative x. Okay. Just making sure that we're all on board. L is still the limit as x approaches 0 from the right, because all we've done so far is just simplify our rational expression. We haven't done anything else. Now we plug that 0 in, and L is equal to 0. We're not done yet. Good call. Therefore, the limit as x approaches 0 from the right of x to the x is equal to e to the 0, because remember this L part, I put natural log in there. You have to counteract it with that e, and anything to the 0 power is 1. Good. You don't have to write the therefore statement. You can just write equals e to the 0, which is equal to 1, but I just want to make sure you understood it. All right, let's do more. Let's do more, because it's so much fun. Okay. All right. Let's do it right now. Here is example 2b. We are going to take the limit as x approaches infinity of 1 plus 1 over x to that x. Okay, what happens when I plug in infinity? This would be 1 plus 0 to the infinity. So this is the same thing as 1 to the infinity. Now, I always get the question, 1 to any power is just 1, right? No, not when we're talking limits, because we're saying, what are we approaching? All right? So it's not always that when you have a limit. Okay. Let's do this thing. So it's a function to a function. So let's introduce natural log. 1 over x. Now, oh my goodness sakes alive, I did it again. Oh, you guys, what's up with me? I can't lose that limit. Where did that little fella go? It's got to be there. Don't go away, limit. We need you. All right. So now this is going to be infinity times 0, right? Because this is going to give me a 0 here, and the natural log of 1 is 0. So infinity times 0. Let's rewrite this. So L is equal to the limit as x approaches infinity of the natural log of 1 plus, I'm going to write this as x to the negative 1 because I don't want to mess with all the other stuff, over x to the negative 1. And now we have a 0 over 0 indeterminate form. Do you see that? The natural log of 1 is 0. This is going to be 1 over infinity, which is also 0. Now we can do L'Hopital. Algebra never goes away, does it? So the limit as x approaches infinity, this will be 1 over 1 plus x to the negative 1 times the derivative of the inside, which would be a negative x to the negative 2 over negative x to the negative 2. That's handy. So L is equal to the limit as x approaches infinity here of 1 over 1 plus 1 over x. Yes, we have a rational expression, but the fact that all of those are 1s, you can see what's happening here. This, let me make this whole thing here is going to go to 0. So 1 over 1 is 1. Therefore, this is e to the first power as my answer. So e is my answer to this one. We started off with an indeterminate form of 1 to the infinity, but did we come up with that as our answer? That's why we have to do this, right? Because e is the answer here, not 1, even though that's what we get. All right. Now, just as a side note, you're going to see this one again. If you want to use brain space, great. If you want to figure it out this way, that's fine too. But note, you will see this again. It's pretty common. If I take the limit as x approaches infinity of 1 plus 1 over x to the x, that equals e. Every single time. Let me make that e better. Every single time. It's e to the first power. So this is a common one, just like the other common ones that you have learned from Calc 1, right? The limit as x approaches 0 of the sine of x over x equals 1. You just know that one now. This is one of those that you could put in that same toolbox that you've got building. All right? Okay. Okay. We'll see it again. It'll be a little while before we see it, closer to the end of the semester, but we will see it again, so I just want to make sure you know. All right, let's do one more, just for good measure here. Let's get out of red. Here's example 2C. We're going to take the limit as x approaches 0 from the right of cosecant x to the x. Yeah, trig. Yeah, it is. Love it forever. So the 0 approaches from the right. There's an asymptote there, right? So it goes to infinity. And then 0 is my exponent, so infinity to the 0. There's my indeterminate form. Let's introduce natural log. All right. So x, natural log. Oh my gosh, you guys. I did it again. 3 for 3. At least I'm catching it. What is up with me today? There it is. As long as you catch it, right? Notice I catch it every time because I'm like, where did my limit go? Oh, there it is. All right. So rewrite this. L is equal to the limit as x approaches 0 from the right of the natural log of cosecant x over x to the negative 1. All right. Now I've got my indeterminate form here, and then we can do L'Hopital. All right, so this is infinity over infinity, right? And I've got L'Hopital. So L is equal to the limit as x approaches 0 from the right. The derivative of the top would be 1 over cosecant x times the inside. And remember, the derivative of cosecant is negative cosecant cotangent all over negative x to the negative 2. Negatives are my nemesis, so if there's a negative and a negative on top and bottom, I'm going to go ahead and cancel those out. Notice cosecant on the top and the bottom there cancels out, and I'm actually left with the limit as x approaches 0 from the right of cotangent x over... Are you okay? If I just do this, because I don't want to write a whole ton of steps. X squared cotangent x, right? That's the same thing. Do you see that? This is 1 over x squared. You move it to the top, so it's up there with cotangent. All right, we're in Calc 2. We can do some of these shortcuts, right? Okay. Now, if I plug in a 0, 0 times anything there is 0, and I have this cotangent. And if I switch this up, right? And I say that this is cotangent, gives me cosine over sine. Let's see if that's helpful. So I've got x squared times the cosine of x over the sine of x. Anything looking good there? You can, yes. So here's the deal. Now that I have this, you can look at this, and yes, this would be 0 times 1 over 0. So that would give you 0 over 0, and you just keep going with a whole bunch of trig. But what else do you know? What did we literally just talk about? That the limit as x approaches 0 of sine of x over x equals 1. I also know that the same thing applies if I have the limit as x approaches 0 of x over sine of x still equals 1. So let's use it. Make our life easier. So I've got the limit as x approaches 0 from the right of x over sine of x, because I'm taking one of those out, times just that x times cosine. And this will be 1 times 0 times 1, right? And then that's how I get my final answer of 0. It's not indeterminate at that point, right? As long as your answer could be 0 all day long. As long as you don't have an indeterminate form, then you're good. So this is the same thing as e to the 0, which is then 1, right? So therefore, my limit as x approaches 0 from the right of cosecant x to the x is equal to 1. If you write that, great. If you don't, sometimes I just get in the habit of doing that stuff. right. Trig's here to stay. All day, every day. Especially in Calc 2, we really hit trig hard. So make sure you know those derivatives. If you don't know your derivatives, make sure you're studying up on them. Make flashcards, do what you need to do because you need to know your derivatives. All right, L'Hopital, we're getting a little limit action back. That's exciting. Okay, go rock the socks off.